Hello, this is Dr. Muhammad, and this is another video under Dynamics of Structure. And in today's video, I'm going to talk about the forced vibration response to harmonic motion damped system. It is the same topic as the previous video, but today I'm going to talk about part 2. So we are going to focus today on some graphical representation of the RD and the phase angle and the effect of damping ratios, different damping ratios, with an example. In today's video, these are the main contents of today's video. First, I'm going to talk about the graphical representation of the response modification factor, of the response modification factor. As we have said, this is RD. And in the same time, I'm going to talk about the phase angle. So as we have mentioned before, it is like phi. So we are going to talk about these two and how we can understand them more based on a graphical representation. After that, we are going to highlight the importance of damping ratios. So we're going to talk about the deformation response factor, which is sometimes we call it deformation response factor or response modification factor. They are like the same. And the phase angle for different damping ratios. So here we are going to highlight about the importance of damping ratios on the phase angle, and the response modification factor. And at the end, I'm going to talk about, I'm going to give an example that is going to illustrate for us what we have discussed about the damped forced system. Now let's go first and understand more about the some annotations that I'm going to use during the graphical representation, and I want you to understand it very well so that you're not going to get confused when I'm going to explain. First of all, sometimes I'm going to put, or in the graphical representation, you're going to find something like this, which is U static and between parentheses node. This actually means, the meaning of it, it is P node over K. It is P node over K. So here this means actually here that P node, which is the maximum amplitude of the maximum amplitude of the force over the system stiffness, So we can define it like the maximum, take care of this word, maximum value of the static deformation, because we are talking about the maximum amplitude of force over the system stiffness. And then we are going to find another annotation, which is U static, as you can see it here. So it is U static here, and between parentheses it is T, as if that there is varying time here. The T is like a parameter here. So we are actually saying that this is a relation between the force, which is sinusoidal force, which is P node sine omega bar T, over the system stiffness. So what is the difference between the first annotation and the second annotation? The first one is talking about the maximum. The second is talking about the static deformation at any time. So here we are talking about the maximum value, the maximum value, of the static deformation, which is related to the maximum amplitude. However, in the second, U static T means that it is what is the static deformation at any time due to only the force, only. They are close to one another, but we can consider U static node, it is the maximum value for the second case. And the third one is going to be U of T, which is the dynamic response. This is the dynamic response, which is going to equal the damping, amplitude, the maximum amplitude. Sometimes the book use U node, so do not get confused. Like rho or U node, it is the same. And then sine omega bar T minus phi, which is the phase angle. And this is, what is this one? it is the dynamic response for the steady state, okay, case varying with time. So it is the steady state, again, steady state response. That's very important of the system, okay? And we are focusing on the part after the transient, because if you remember that we have the other parts that we were talking about, and then we said that there is something that is going to be after the transient. We are going to have the steady state where that the response is going to be steady, right? This is what we are focusing on. Okay, so now these annotations, I hope that you do not get confused while that we are giving the presentations, okay, or the graphical representation of them. Keep them in your mind, and whenever that, I'm going to like revisit them from time to time to remind you of them. Okay, now let's go to the graphical representation and see how we are going to deal with it. So we are going to have the graphical representation for the deformation response factor and the phase angle. So as I said before, this is RD, this is phi. Okay, so the equation of motion is going to be written, the general solution is going to be written or going to be represented graphically, okay, for different cases, okay, for 3 different values, okay, of omega over omega n. So let's go now and look, because this graphical representation is important for us. First of all, the horizontal axis, as usual, it is t over t. Okay, we understand what is the meaning of t. Small, it is the elapsed time. This is the elapsed time, and this is the natural period of the system. And we have here, we are representing the steady state response. Remember that we are under damped system. This is this video and previous video talking about damped. And we have damping ratio 0.2. Consider this very well. It is like high. This is considered to be high damping ratio, okay? Like 0.2, 20%, okay? And we are talking about sinusoidal force. Remember that we are having a sinusoidal force, means that our force is something like this. This is the forcing term, the excitation function that we have. Okay, for 3 different values, of, let me remove this part here. Okay, for 3 different values of frequency ratio. So we are having 3 different values of frequency ratio. So we have omega over omega n 0.5, and omega over omega 1, and omega over omega n equal 2. So what is the meaning of this? Is there a kind of like something that we should be taking care of? Yes, the second one is what? Exactly, there is resonance here. So this one, we are going to find resonance, okay? Okay, resonance. Here, this means that our forcing frequency is only half of the natural frequency of the system. Here it is the opposite, that the forcing frequency is double the natural frequency of the system. So we are going to have, like, we are having 3 different cases, okay, where that the natural frequency of the excitation, the excitation frequency is half of the natural frequency. And the second case where that the natural frequency equal to the forcing frequency, and the third case where that the forcing frequency is double of the natural frequency. Okay, so like we are having different cases here. Okay, so let's go to the first part, which is omega over omega n equal to 0.5, and put our steady state. Remember, we are talking about steady state response. Forget about the transient now. Forget about it. Already we are talking about the steady state response only. Okay, of course we're talking about damped system. Okay, now let's go to the first part. The first part is, which is A, omega over omega n equals to omega over omega n equals to 0.5. This means that the forcing frequency is, like, as I said, it is half. So if we have like the forcing frequency of the force, it will be something like this. However, that the frequency of the system might be like larger, something like this. Okay, so now let's look to the response. As I said, the horizontal, let's put it again, the horizontal here is T over T, and the vertical, it is as usual, as we have put it many times before, it is UT. Remember, this is UT, the dynamic amplitude or the dynamic response. This is the static response. Okay, again, what is UST node? Let's go back and yes, U static, this one, U static node, P node over K, the maximum value of the static deformation. That's what we are talking about here. That's the maximum deformation of static, or the maximum value of the static response, right? Okay, now let's see. We have two different lines. The solid line, which we call it the dynamic response, which is UT, as you can see here, it is U of T, the dynamic response, over U static node. This is giving to us the dynamic, or the ratio between the dynamic response and the maximum static response. However, the dashed line, it is giving to us what we call it the static response, which is U static over U static node. I do not want you to get confused. If you do not know what is the difference between U static of T and U static node, then let's go back and look to this. Here, U static node, the maximum value of the static deformation. U static at any time t, it is P node sine omega bar t over K, which is the static deformation at any time. Okay, so this subscript node means that the maximum value, okay, for the static deformation. The other one, which is having t between the parentheses, it means at any time. The static load, the static deformation at any time, it will be changing with time because we have sinusoidal function of the forcing excitation, right? So it is going to be high, low, zero, and so on. But here U static, no, it's not. It's always maximum. So we are talking about, I hope that you get the meaning. This is dynamic. This is dynamic. This is static. Again, dynamic, which is changing with time. Static also, it is changing with time because we are talking about U static of T, which is related to the forcing excitation. It is static in its nature, but it is changing with the sinusoidal function, which is sine omega bar T P node. This is the force, the forcing term, P node sine omega bar T. So it changed with time. Our applied force is changing with time. So we are comparing between the two. Okay. So now I want you to imagine this, that we have response of the system, which is the solid line. This is the response of the system, the solid line here, which is moving on it now by the red color. And the other is the static force. Consider the dashed line as the static or the static response, or consider it as the forcing excitation. The forcing excitation. Okay, so let's clean. I want to clean this now because I want everything to be clear for us. Okay, when we are going to make this, we found that the solid line is going to, as you can see here, having some there is a difference on the horizontal axis, as you can see, and it is measured here, like here, phi over 2 pi equal to 0.04. What is the meaning of this? This means that phi, it is going to be almost going to be like 0, right? Means that the phase angle is going to be almost the 0. They are going to be similar to be said they are in phase. What is the meaning of phase, or in phase in this case? This means that the maximum of the total response, dynamic response, is going to be almost the same as the maximum force. They are going to be in the same time. When the forcing excitation is going to reach its amplitude, which is 1, our dynamic amplitude is going to reach the maximum as well. Almost. They are having some difference here, as you can see. This difference is this difference. Very small. The phase angle is very small, as you can see, and you can find it here from T. Okay, almost two of them, they are having the same the same T. And let's go and see what is, remember we are talking about RD and the phase angle. Okay, when we put our phase angle, or when we put omega over omega n equal to half, we found that for the first case, RD is going to be 1.29. What is the meaning of this? Remember, RD, it is going to be the horizontal axis. This is the maximum value that we're talking about here. 1.29. What is the meaning of this? The meaning is the dynamic response is going to be higher than the static response by 29%. That's the meaning. That's the meaning. This means that there is dynamic amplification for our response because of the dynamic response of the system. Okay, so this is the case where that omega over omega n equal to omega over omega n equal to 0.5. Okay, now let's go and see the case where that we have omega equal to omega n, where that we have resonance. Okay, first of all, in this case, we are going to have, look here, there is seemingly to be, we're having something for the phase angle, right? It seems that the maximum amplitude of the solid line, which represents the dynamic amplitude, is like is having some, or not lagging, it is the dashed line is lagging behind the maximum amplitude, or the response of the dynamic response of the system. Okay, there is a difference here. This is here. This is the difference. This difference is phi over 2 pi equal to 0.25. Okay, 0.25, which is like large enough. Okay, that is large enough to say that they are not in phase. So what is the physical meaning of this? When the force reaches its maximum, the system is not responding. Can you imagine this? The system is zero, means that there is no response on the system. If this is the single degree of freedom system, and we are going to apply the force here, which is sinusoidal, P node sine omega bar t. When this force reaches its maximum, okay, the system will not be going here or there. It will be in the neutral position. Okay, it will not go here or here. However, when the force is going to be decreasing, as you can see, we're going to find that the response is increasing, right? This is the meaning of the phase angle and the meaning of the time lag between the two, because we have a time, or we have phase angle here, which is phi over 2 pi equal to 2.25. This means, the meaning of this means that we have phi almost pi over 2. Okay, this means whenever that we are having maximum force, the system is zero. Okay, there is no response here. And when the force is reaching zero, the system is maximum, reaching maximum, as you can see here. Okay, that's very nice. Let's go now to the last part, which is, what is the relation between the two? We are interested always in the solid line, the maximum value. Look to the maximum value here, which is the maximum amplitude on the vertical. okay, in the vertical axis, as you can see here. We found that RD equals to 2.5. What is the meaning of this? The physical meaning. What is the physical meaning of this RD equal to 2.5? It means that the dynamic amplification of the system due to the dynamic effect is going to be like 100%, 150%, okay, increasing by 150% of the static force. So if the static force maximum is here, okay, let's assume this is, for example, 1 inch, then our system dynamic response is going to be 2.5 inches, for example. Okay, that's the meaning here. This means that resonance is working now. The amplification of the amplitude is there. Remember that we are talking about damping ratio equal to 2.2. This is, in the example itself, we said about this, that we are talking about damping ratio equal to 0.2, right? This means something horrible, that our force, our response is going to be, the meaning actually, if that, if we have this is the single degree of freedom system and we apply the force here, then we are going to find that this force which is being applied is going to make maximum, okay, this force, if it is applied statically, okay, statically, then it is going to make, for example, like 1 inch. But if we leave the system to respond dynamically, we are going to find that this system is going to reach, okay, is going to reach values of the response that is reaching almost 2.5 inches. Okay, that's the meaning. So the difference between the solid line and the dashed line is the solid line, the force is applied on the system and the system is dynamically responding. The dashed line means that the system is under the application of a static load that is changing with time. Okay, so the response of the dashed line, it is the static response, okay, due to the change of the force under the time. Okay, there is no dynamic effect in the dashed line. Okay, that's the meaning here. Okay, now let's go to third part. I want only to remind you with something important here, which is the dynamic amplification factor. In the first case, it was 1.29, which is 30% almost more. Here, we are reaching 150%, right? Let's go to the third case. In the third case, we are going to find that something very interesting, that we are having the phase angle, this phase angle almost, we are having almost, it is going to be equal to pi, right? And you are going to find the solid line is almost in phase, right? The maximum response equal almost the maximum static response, or the maximum amplitude of the force would be in the same time with the maximum response of the system, right? As you can see here, they are zeros together, they are having the same and so on. And one of the most interesting part is RD. Look to RD. Exactly, it is less than 1 for the first time. It is 0.32. Means what? The response of the structure is being like damped. It is going to be reduced. It's not amplified. It is not amplified. The response of the system due to the application of the load is going to be less than the static response. Okay, less than the static response. So if the static response is going to give us like 1 inch, for example, then the dynamic effect would make this 1 inch to be less. It will be here and it will be here. Can you imagine? So this is the beauty of the dynamic effect here. It works for our side now. It works for us. It works in our side. Okay. So now this is 0.32. Okay, this is the case where that we are having omega over omega n equal to 2. Whenever that we have a very high excitation frequency, because here this is the excitation frequency here is very high compared to the natural frequency. It is double of it. So it is preferred for us, if we are going to design our system, to choose the amount or to design the structure based on the excitation frequency. If we know the excitation frequency, then it's better for us to make the natural frequency of our system to be like half of it. Okay, so we're going to have that suppressing of the dynamic effect on the system itself. Okay, so this is very interesting. I think that like graphical representation that is giving to us what is the meaning of deformation response factor and what is the meaning of the phase angle. Remember well that whenever that we have phase angle, that is, they are out of phase. Here we can say that this system is out of phase. Okay, means that the maximum of the force is going to be like counteracted by the maximum in the opposite direction of the dynamic response of the system. So they are suppressing one another. This is why it is 0.32 here. But if you go up, you're going to find that both of them, they are working in the same time. The maximum amplitude of the excitation force, it is in the same or in phase with the maximum response of the structure. And the worst case scenario happened when we have omega over omega n equal to 1. This is the resonance, where that we are going to have our RD equal to 2.5. Okay, now we are going to talk about the graphical representation of the deformation response factor, which is RD, and the phase angle, which is phi, for different damping ratios. So we are going to have different damping ratios, and let us see how we can work with this. So actually it is the graphical representation is a little bit huge, but I want you to understand it. You can find it easily in the textbook also. So first of all, the horizontal line is going to be the frequency ratio. It is going to be the relation or the ratio between omega n and the omega, which is the forcing excitation frequency, and omega n, the natural frequency of the system. And the vertical axis, we are going to have two different vertical axes here. Okay, if we're going to talk about the first graph, it is related to, as you can see, the deformation response factor, which is RD. So simply, this is RD, which is, as I said before, U node over U static node. The maximum dynamic amplitude over the maximum static amplitude. Okay, so this is the first case here, the first graph. Let me make it a little bit smaller so that we can see. Yes, that's it. Okay, so this is the first case where the relation between the horizontal line is going to be, as I said, which is the relation between omega bar over omega n, and the vertical is going to be RD. And the other graph, which is commonly attached to the first graph, it is going to be related to the same horizontal axis, omega over omega n, but the vertical axis is going to be phase angle. It is going to be the phase angle. Okay, going to be the phase angle. Okay, so now we are going to analyze this. We are going to analyze these graphs because they are really important for understanding. So this graph called the deformation response factor and phase angle for damping system excited by harmonic force for different damping ratios, as you can see. So first of all, let's go to this part, which is related to the RD and the damping ratio. If you look here, you're going to find the horizontal line. Let's go here. The horizontal line is having 0, 1, 2, and 3. This means that we are having at 1, it is very critical for us. This means that 1 means what? Omega over omega n equal to 1. This means that resonance is going to take place here. So we're going to find it's very special here. And here it is 0, means that the frequency of the force is going to be very small, okay? And almost 0, means that it is going to, as you can see, there is no excitation frequency there. Okay, so in this case, if we're going to look to this and describe what we are seeing here. First of all, the magnitude, what we can see from here, that the magnitude of the reduction is strongly dependent on the excitation frequency, right? Because if we're going to talk about RD, if we are talking about something small here, then you are going to find that the RD is almost reaching 1, right? This means that there is no dynamic amplification at all, right? And if the omega bar over omega n is reaching to 3, this means that the system, as you can see here, is reaching very small value for RD, means that the response is almost like vanishing. It is suppressed, right? Why? Because if the applied frequency of the excitation force is very high, this means that the system is going to respond. As you can see here, RD is going to be very small. The dynamic amplification or the deformation response factor is going to be very small. Okay, so that's one of the interesting things that we have found in the previous graphical representation. At 2, do you remember we said that at 2 it was very small. RD, we're reaching RD equal to 0.32 before, right? Do you remember? This is in the previous one. So if we are going to increase this omega bar over omega n, sorry, we are going to decrease it going here toward resonance, you are going to find that the response modification or deformation response factor RD is going to be increasing exponentially. And it has something to do with the damping ratio. If we have very small damping ratio, it seems that if we're talking about something here, for example, then you're going to find that we are having very large RD. However, if we have less or higher damping ratio, we're going to find at the same point here, for example, it is here less RD. And if you are going to have higher damping ratios, you're going to find that the RD is getting like decreasing, right? And if you are going to have like 0.7 or 1, for example, you're going to find that the RD is going to be less than 1. It is going to be 0.4, which is something very interesting for us, and we have experienced this in the previous case. Okay? Okay, so now let's examine these parts and try to think about them clearly. So here, let me like clean first these parts here, okay, so that we can understand what we are talking about in clear way. Okay. Okay, first of all, if the frequency ratio, let's assume that if the frequency ratio, this ratio, if the frequency ratio omega over omega n is very small, less than 1, this means what? Less than 1. Okay, this is 1. It is less than 1. This means what? T is very large compared to, here means that T is very large compared to Tn. T bar, which is for the excitation, very large compared to the Tn. Okay, right? What is the meaning of this point? That we have the forcing excitation natural period is very large. Okay, then you are going to find that implying that the force is slowly, this is what I want to highlight here. The force is slowly varying. The force is slowly varying in this part here, less than 1. Okay, what is the meaning of this? Can you imagine? Just you can close your eyes and imagine that the force is slowly applied on the system. Okay, so RD is only slightly larger than 1 and is essentially independent of damping. You're going to find that here, 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 it doesn't, there is no difference, almost no difference between what is the type of damping that we have. It doesn't matter, because here really it doesn't matter. Damping does not matter here in this case if we are having omega bar over omega n to be very small. Okay, why? Because we are going to have U node in this case. I mean, we're talking about this case. Okay, U node in this case, which is almost equal to U static node. The dynamic amplitude would equal to the static amplitude, maximum amplitude, and equal to P node over K. And here the result implies that the amplitude of the dynamic response, as we are talking about, is essentially the same as the static one, right? That's right, the static deformation. And it is controlled by the stiffness of the system. Here, remember that the stiffness of the system is going to be the main controller for this. So if we are going in a place or in the region where that the T is very large compared to Tn, means that omega bar over omega n is very small, which is this case here, we are talking about this case, then we are going to find that our equation that is controlling is this equation. What does it mean? The dynamic amplitude, maximum amplitude, equals to the maximum static amplitude, and we are going to find P node over K. This is the ratio. Where's the remaining part? Sine omega bar T? There is no, it is the maximum here. So the system is going to, we are going to control the response based on the stiffness of the system. Okay, so it is strongly recommended that if we have omega bar over omega that is very small, then it is very important for us to design our system with stiffness. Take care of the stiffness when you are designing your system. You can control the response of the system by controlling your stiffness. Okay, if the stiffness is going to be very small, then your system is going to respond very high. If the stiffness is going to be higher, then the response is going to be lower. Okay, so this is very sensitive. This part is very sensitive to the stiffness of the system. Okay. Okay, now let's go to the second part. I want to clear everything because I think that it's very messy now. Okay, erase all ink. Okay, now let's go to the case where that we are having omega over omega, omega bar over omega n, that is going to be very large, larger than 1. This means that T is smaller than Tn, right? We are talking about this part here, right? Implying that the force is rapidly, so force, I'm going to write this, force is rapidly applied. Okay, force is rapidly applied. Close your eyes and imagine this, that the force is rapidly applied. The frequency is very high and the system is like receiving the force in a very rapid way. Okay, this means that RD, let's go, we are talking about which range that we are talking about. It's much larger than 1. We said that this is here 1 and it's much larger, which is we are talking about this area here, for example, here. So first of all, do you think damping would make any effect here? Just think for a couple of seconds. The answer is no. As you can see, all damping ratios, they are the same here. It is very similar to this part also, right? So they are the same. Okay, so RD tends to be what here? RD tends to be what? 0. It tends to be 0. Means that the dynamic amplification factor is going to, or the maximum dynamic amplitude is going to vanish. Almost nothing there. The response of the system is very small. And it is essentially unaffected by damping. So there is no damping issue here. The damping is not there. For large values of omega over omega n, okay, we are going to find that our system is going to be dominated by the mass of the system. Actually, it has something to do here with our case, because here we have U node, which is the maximum dynamic amplitude. It is almost going to equal to U static node, which is the maximum static amplitude, right, times omega n squared over omega squared. Okay, this would equal, if you apply on the equation, you're going to find this equal to P node over m times omega squared. Okay, what is the meaning of this here? Because you are going to find the term that is going to be controlling. Let me highlight this. I'm going to find m is going to control the system here, because actually P node and omega, which is omega bar, we're talking about omega bar here, both of them, they are related to the excitation, okay, force. However, m, it is related to the system itself. It is related to the system itself. This means that if you want to control the dynamic response in this region, where that omega bar over omega n is very high, larger than 1, you need to control the mass of the system. You need to control the mass of the system. Okay? That's very, very important, and you need to take care of this in your design. Okay? Examine this part which is related to omega over omega n, because maybe it's not clear for you how the mass is going to be controller. So in case of omega over omega n, omega bar over omega n larger than, very large than 1, in this case I'm claiming that U node, which is this U node, as I said many times, it means that the maximum dynamic amplitude, which is rho, okay, equals to the maximum static amplitude times omega n squared over omega bar squared, or omega squared, which is equaling at the end P node over m over omega bar squared. And I said that it is going to be, m is going to be our controlling parameter here related to the system, because the other two elements, they are related to the force itself. It's out of our hands. But if you are going to design, you're going to design the mass of the system, or you're going to control the system itself, whether it's the stiffness or damping or mass. So in this case, we are having mass to be the most important parameter. Why this happens? If we go back to the steady state case, as we have mentioned a couple of videos before, please revisit like 2 videos before, we said that the maximum dynamic amplitude is going to equal RD, the deformation response factor, okay, times the maximum static response. That's right, because we are like magnifying, decreasing or increasing this static response based on the RD, right? Okay. And if you remember that we said this, the dynamic response or response modification factor is going to equal this U static times this RD here. It equals to 1 over the radical, the big radical here. We have the radical here, and we have omega bar over omega n raised to the power 2, and then it is going to be raised to another power 2 plus another term here. Okay. When you look to this equation, you are going to find that this term, okay, this term is going to be dominant. It is going to be dominant. So if we are going to look, you are going to remove the radical, okay, and with the power of 2, then you are going to find that this term, which is 1 minus omega bar over omega n to the power 2, is going to be the dominant here, not this term. This term is going to be only the ratio. Here it is raised to the power 2. So we are going to claim that rho equal to U static node, okay, times this term, which is the reciprocal of omega bar over omega n. It will be omega n over omega bar, both raised to the power 2. Okay, both raised to the power 2. And here, u static node, it equals to p node over k. And this one, we know that omega n equals to omega n to raised to the power 2 equal to k over m, right? And over 1 omega bar n, right? This is the flow of the equation. Then from here you can find that k cancels out this k, and then we're going to be remaining with p node over 1 or over m times 1 over omega squared 2. This means that the final maximum dynamic amplification is going to be function in two things: something related to the forcing excitation and something related to the system itself. This is what I'm talking about, and this is what I was claiming in the beginning, that this is related to the system. Okay, this is related to the system. So here in this case, where that omega over omega n is very large, larger than 1, mass is going to be the main controller for us. Mass is going to be the main controller for us, and this is the definition of what I have said. Now let's go back to what we were discussing before. Okay, so that you are I think that now you can understand what I meant by this equation. Okay, so this is the case in the second case, where that we are having this mass, where that we are having the omega bar over omega n larger than 1. Now let's go to the next case, where that we are having omega over omega n almost equal to 1. Almost equal to 1. Or in that case, where that we are going to have omega bar over omega n, it is going to be almost 1. This means that we are in the resonance case, right? This is because this is omega bar over omega n, and here we are having 1, right? So the forcing frequency is close to the natural frequency of the system. Okay, and in this case, RD is going to be, as you can see here from the graph, it is going to be very sensitive. Okay, it is going to be sensitive, okay, to the damping ratio. RD is going to be very sensitive. So if we have 0.2, it is going to be very largely different than 0.1. RD is going to be very sensitive to the value of the damping ratio. So if we are in the range around this part, which that, as I said, omega bar over omega n equal to 1, here we are going to find ourselves that RD is very sensitive to the damping ratio. And RD can be several times larger than 1. As you can see, here it is 1, here it is 2, 3, 4, and we can go larger. So it is very sensitive in this case, and we should take care of this. This means that whenever you are designing your structure, you need to avoid having omega bar equal to omega n. Try to avoid it. Try to go outside of this part as much as you can. Okay? And in this case, we are going to say that damping is the most important, the most important factor here. Damping is going to be the most important factor in this case. Okay, so we have now the final thing is that if we have, remember that very well, that damping in this case is going to be the dominant or going to be the most important factor, because we are going to have U node, which means that the maximum dynamic amplitude, it is going to equal U static node, okay, over 2 damping ratio. Revisit what the equation that I have used before. So it equals to P node over C, which is the damping coefficient, times omega n. So here you are going to find C is there. This means that our system is going to be related to damping. Damping is going to be controlling here. Damping is going to be controlling here, as you can see from the graph. Okay, so based on that, we can conclude like this. If we have omega bar over omega n, okay, is going to be smaller than 1, very small, this means that the force is slowly varying. This means that the deformation is controlled by what? Exactly, by stiffness. That's very important. However, if we are going to say that our omega bar over omega n is very large, then the deformation is controlled by what? Exactly, as we said, it is going to be controlled by mass. Mass is going to be our main controlling parameter. But if the case where that we have omega bar over omega n is around 1, this means that resonance case. This means that the deformation is going to be controlled by damping. Okay, damping is going to be our main factor that we are going to have here. So the damping is going to be the main controller. So remember that very well from the curve. Okay, we have 3 different cases. Remember that based on each case, you can design your system. Okay, whether it is, and all of them, they are related to omega bar over omega n. So you need to control it, or you need to control your system. If you need to control them, then you need to look to what is the ratio between omega bar over omega n, and based on that, you are going to control the main important factor. Here it is the stiffness, here it is the mass, here it is the damping ratio. Okay, so here for the case of the frequency ratio with respect to the phase angle, you can see from here that if we are talking about omega bar over omega n, it is going to be very small, larger than very small, smaller than 1. Means we are here, okay, in this range. What you can see here, the phase angle is going to be almost 0. This means that we are in phase. Again, what is the meaning of in phase? This means that the force and the response are going to be the same. Okay, means that when the force, okay, going to act on the right, for example, okay, if the force is acting to the right, the system is going to displace to the right. They are in phase. Okay, that's the meaning of in phase. However, if we are going to have omega bar over omega n that is larger than 1, this means that, as we said before, the force is rapidly varying. You're going to find that phi is close to 180, and the displacement essentially is out of phase. So we call it out of phase. This is out of phase. So this means that here at this range here, okay, where that omega over omega n is very large, you're going to find that it is out of phase. Okay, out of phase. What is the meaning of this? It means that when the force acts to the right, the system would be displaced to the left. Okay, so that's the meaning of out of phase, where this is our system. The force is applied in this direction. You're going to find that the system is displaced in this direction, opposite to the direction of the force applied. This is P, and this is the system. Okay, and at the end, whenever that we are having omega bar over omega n, they are almost equal to 1. In this case, you are going to find something very unique. This is the case. The forcing frequency is equal to the natural frequency. So this is almost at the case where that phi equal to 90, as you can see here. This is 1, and you're going to find that phi equal to 90. pi over 2. This means that for all values of the damping ratio, you're going to find that the displacement attains its peak when the force passes through zeros. You cannot write it, it's in phase or out phase. It's not like this. It is, if we go back, do you remember that this is the force? However, okay, this is the maximum here at the force. Okay, the displacement, as we said, the displacement attains its peaks when the force passes through zeros. If this is the force, so the system is going to have its peak here. This is the peak of the response. Okay, and so on and so forth. So it's something that is unique. Zero force, maximum response. Okay? Okay, similar to what we have explained before. If I go back here, maybe we can find something. I think yes. Yes, I think this is the second case here, this case. Okay, this is the second case where that phi equal to pi over 2. Okay, so now we are already reaching the end. Okay, so let's have an example here. We are going to have an example, okay, from Mario Paz 5th edition. So we are going to find that in this example that we have a structure, as you can see here. It's a single degree of freedom, like single story structure, and it has mass of 15 kips here, and there is force applied on the system. This force, it is changing with time. F of t equal to 200, which is the maximum force sine, okay, 5.3 t. This is the forcing or the excitation function, okay, and the displacement of the structure in the right direction. Okay, so we have the mass now equal to 15 kips, okay, and we have the force, as we said, this is F of t, which equals to the amplitude 200 times sine 5.3 t. Okay, and we are having a supporting rotating machinery that exerts horizontal force, which is already, we talked about it, at the girder level. Okay, this is the force that is being coming from the this machinery, assuming 5% of critical damping. So our critical damping is 0.05. It is 5%. Okay, then determine the following. First, we need the steady state amplitude of the vibration. We need the amplitude, steady state amplitude of the vibration. And B, the maximum dynamic stress in the columns. Assume a girder is rigid. Okay, take care of these words. Okay, let's see how we are going to start our solution. Steady state amplitude, if you remember, our steady state amplitude, which is going to be this rho, right? It is going to be U static node, okay, over, okay, 1 minus omega bar over omega n. I'm going to call it R, okay, because it is really like annoying in writing it. Okay, plus 2, and here this is R times damping ratio. All of them are squared. Okay, damping ratio, all of them are squared. Okay, so now we are having this, okay, where that I'm going to write that where R equals to omega bar over omega n, as we know. Okay, so then we are going to start with the solution. The structure may be model. As you can see, this is our structure. It's a single degree of freedom system, okay, like this, or commonly we can put it in this mechanical, or this is the mechanical people like to put it like this, like a trolley, and there is K and there is C. Okay, the columns, they are having wide flange 8 by 20, means that everything is known for it. So the section modulus and everything is known. Okay, and the height, it is known for us to be 15 feet. So everything related to the structure is known. This structure may be modeled by dynamic analysis as for dynamic analysis as the damped oscillator shown that we already used before. The parameters in this model are computed as follows. First of all, we need to know what is the stiffness of the system. Okay, what is the stiffness of the system? We have here our system can be modeled like this: hinged here, fixed here. Why? Because this is already given in the example. Look here, it is hinge, and in the top it is fixed because already there is a keyword given in the example, which is assume the girder to be rigid or is rigid. This means that the girder is large, is having a large stiffness compared to the column stiffness. So we are going to assume it as fixed hinged as here. For fixed hinged, K is going to be 2EI 2I over L to the power 3. This is L, which is the length. 2I because we have two legs, right? We have two columns here and here. So we are having two columns because we are talking about the system itself. Okay, it is hinged here, so we have this I and this I. Okay, we know the I of the system. Okay, we know this I because we know the cross section of the system, wide flange 8 by 20. Okay, so if we're going to substitute for this is what we call it the unit displacement at top of pin support columns requires force equal to 3EI over L cubed. I think that you know it from structural mechanics. When we are going to substitute with everything here, we know that is E. It is supposedly to be known for us. Okay, if you want it. Okay, so this E, it is. We can put it, actually everything is going to be known. For example, I column, it is given to you for like it is 69.2 inch to the power 4, and Young's modulus for steel, we know it 30 by 10 to the power 6 pounds per inch squared, and the gravitational acceleration equal to 386 inch per second square. These are some information. Supposedly it is known for us. Okay. Then our damping ratio, it is given for us by default in the example. Damping ratio is 5%. Take care of that. We put it like 0.05 here. This means that our maximum static amplitude is going to equal what? The maximum force amplitude, which is 200, okay, over the static stiffness of the system, which is already we have calculated from the previous step. So we are having 200. From where this 200? Exactly here. This is the amplitude of the force, right? Okay, and then we have this K, which is already has been calculated in the previous step, which is 2,136 pound per inch. Okay. Based on this, we now want what? We want to calculate this R here, okay, which is omega bar over omega n. So we need to calculate omega bar and omega n. So based on this, our omega, which is the natural frequency of the system, please take care because here I'm talking about Mario Paz. So actually he's using omega as the natural frequency. So I'm very sorry for this, but take care. It is only like take an example from the book. So they are not having the same annotation. Okay, or maybe you are going to surprise here why it is omega. It is supposed to be omega n. So consider this as omega n, okay, according to our common traditional annotation. So omega n equals to the square root of K over M. So we have K, we calculated K already. Take care. So, and we have the mass, which is 15,000 kips, and divided by the gravitational acceleration to get the mass. Okay, remember that the weight equal to mass times the acceleration. So here we put this acceleration in the numerator, and we have K here. Then we are going to have our natural circular frequency of the system, which is 7.41 rad per second. Okay. After that, our ratio, which is R equal to omega bar over omega n, and this is known for us, 5.3. From where? Go back here, and you can find this is 5.3. This is omega bar for us. Okay, then you can like solve for, this is omega bar and this is omega n from the previous step that we have here. Then we can have it, the ratio is 0.715. This is the ratio. The steady state amplitude from our equation, okay, this is from our equation. This is based on in the book Mario Paz, but for our equation it is the same. This is what we are dealing with, the same. U static node over 1 minus r squared to the power 2 plus 2r damping ratio squared. This gives us 0.189 inches. Okay. Then the maximum shear force in the column is going to be, yes, that's the right thing, which is 3 EI over L to the power 3. Okay. This is the shear force times the maximum static maximum amplitude, because here we are talking about, we want the dynamic effect. So if we are going to use this only, this is the maximum shear in case of the static maximum amplitude, right? But actually our case is not like this. We are having something else here. We have dynamic effect. We found that the dynamic effect is going to like have an effect here. Okay, for unit displacement, our system is going to have or going to require 3EI over L to the power 3. But for 0.189, okay, of the unit, this means that we need to multiply by U here, okay, which is 0.189. You understand? So because this is the definition of the maximum shear, it is the shear stiffness. So here this is per unit, but we are having dynamic, the dynamic effect makes us work with 0.189, okay, inch. So we need to multiply by it. Based on this, the maximum bending moment is going to be V maximum times the height, because we are talking about like here. So this is the maximum base shear. This is the V, supposedly V maximum, that is going to be developed here, right? Even that it is going to be developed at, sorry, it is not going to be on the bottom. It's not excitation at all. That we have something here that is making, sorry for this, we have the machinery here and so on, that is rotating machinery that is making this base shear. So the base shear times L is going to give us the moment, and after that at the end we are going to obtain the stress, which is going to be M over I times C, the common stress, or from structural mechanics you can understand this point, M over I times C. You can obtain the maximum stress on the column. Okay, this is just a rapid example. I want you to stop it here and try to think about it more and think about the flow of the example. It's very easy and straightforward. Just I wanted you to understand the idea of what we have been talking about up until this point. Okay, I think this brings us to the end of this video. Thank you very much and see you in the next video.